Hey everyone, thanks for joining. This is Sunny Beatty, and I'll be talking to you today about how to make your Ruby code faster with multithreading. So big shout out to Shajan for helping me set this up. It's been a huge help. As I mentioned before in the description of this talk, this is definitely meant for more advanced students. So students in the advanced electives, students who are preparing for a Capstone, or students who are kind of in the job search right now. The reason I say that is because this is definitely a topic you might find in a job interview. So concurrency and multithreading are definitely topics that can be thrown at you in a job interview. So this is a great presentation for that. With that said, definitely any students can feel free to join as well if you're making your way through the backend course or in the front end course as well. Definitely feel free to listen if this interests you. Don't worry too much if the topics go over your head a little bit. Feel free to ask a question. I'll definitely get to you when I can. So let's dive into it. So the key takeaways that I want all of you to kind of get from this talk are the differences between processes and threads, the difference between concurrency and parallelism, and finally just how to use multithreading to speed your code. And so this will involve talking about race conditions and also how to use mutexes to prevent race conditions and to make your code more thread safe. So to start off with, it's definitely, if you want to talk about multithreading, we're going to need to talk about the difference between processes and threads. So what is a process? So the way I like to think about processes are essentially programs running on your computer right now. So right now you're using Zoom. A computer is using a process to run Zoom. Same with your web browser. It uses processes to run your web browser. Whenever you run a Ruby script in your console, if you do Ruby and the file name, it spins up a process to run that code. And then the number of processes that are running on your computer is determined by how many computer or CPU cores your computer has. So if you've ever heard the term like Intel dual core or quad core, all those fancy terms, it's essentially just talking about how many cores your computer has. And so each core can run one process at a time. So if you have 4 different cores, you can run 4 processes at once. And so you can even look at this on your computer. So if you go to your terminal, you can run this command, psaux, to find all the processes running on your computer. So let's do that right now, actually. So if I were to run psaux, so ps is just running, it just shows you all the different, lists out all the different processes, and aux are just flags to show all the different processes that are happening. So here are all the processes running on my computer right now. And so as I mentioned before, Zoom is using a process to run it. And so if I search for Zoom, and so I think there's a couple different Zooms. Yes, right here. So this is the Zoom that I'm running to run, or this is the process right now that's running Zoom. And so one other thing you might notice is that Google has quite a few processes right now. And that's because Google Chrome is quite a memory-hungry browser. So it uses a lot of processes to run Google. So I can even show that to you if I do psaux and grep for Google. So this will search for Google. So these are all the processes that are running Google Chrome. So another reason why I want to show you this is because you can see right here, where did that go? It went somewhere. Okay, right here. Number of threads. So this is kind of a nice segue into the next portion, which is what as a thread. So a thread is essentially a subunit of a process. So a process can run multiple threads. So you can see here, this process is running a thread. Sorry. And so these processes can run multiple threads. So that kind of segues into the next portion, which is what are threads? And so the way I like to think about threads is, or the difference between threads and processes, is the process essentially is the boss, where the threads are all the workers. So whenever a process is spun up, you start with one main thread. And so, however, you can still spin up more threads if you need it. So these threads, so basically you can delegate more tasks to run by these threads. And so each thread has kind of 2 major components. You have the stack, which is essentially whenever a thread calls a function, it's going to add that function to the stack. So if you ever see an error or a stack trace in like JavaScript or Ruby, that stack trace is showing you the stack at that moment in time. And also each thread also has a heap. And so the heap is where you store all the memory. And so whenever you declare a function, whenever you declare a variable, those are stored in the heap. And as you can see, all of the threads under one process share the same heap. And so each thread has access to the same bits of memory, the same variables as each other thread. So this will come into effect later on. So one question you might have is, why would someone use multithreading? What's the purpose of it? I kind of mentioned it a little before, but it's usually meant to delegate multiple tasks to different processes or different workers. So let's say I had a really memory intensive program and I need to get a lot of tasks done. There's a lot of data that needs to process. Well, I could, just use the main execution that comes with every process, but that'd be kind of like having a boss who has 50 different things and giving them all to one worker. What we could do instead is just employ 50 workers to run all those tasks. So if you have all those tasks being run at once by 50 different people, it's going to make it much faster. So that is the idea of multithreading and also concurrency. So concurrency allows your programs to run faster. So that's the next thing I want to get into is kind of the difference between concurrency and parallelism. And so you might hear these terms used interchangeably, and they are pretty similar, but there's a big difference between them. And the reason why I bring it up is that we're going to be talking about concurrency and parallelism later on in this talk. So the easiest one to define is going to be parallelism. So parallelism are essentially tasks that are completed in the same time. So all of them are completed at once without pausing or switching and without stopping as well. So you can see this little diagram right here. You have the main thread running and it spins up 3 different threads. And each of these threads are all running and working at the same time. So you have all these little red lines showing the work it's doing. And this is z-axis is time. So each thread starts and finishes at the same time, and they all are doing work at the same time. So this is parallelism because it's all happening in parallel. You can contrast that with concurrency, where concurrency is just tasks that overlap each other. They might be running kind of next to each other, but they're not necessarily running in parallel. So you can think concurrency, something that's concurrent is not necessarily parallel, but something that is parallel is also concurrent. That's a way of thinking about it. Another way of thinking about it is if you have 2 different people doing 2 different tasks at the same time, that's parallel because they're each working on a separate task at the same time without stopping. However, if you have one person switching tasks, that's concurrency. Because even though that person is doing 2 things at once, essentially, they're only ever doing one task at one time. They constantly switch back and forth. So that's concurrency versus parallelism. So hopefully that makes sense. And so since this talk is definitely focused more on Ruby, I have to go a little bit into the details of Ruby concurrency. So the standard version of Ruby, which is known as the MATS Ruby interpreter, so basically the Ruby runtime that MATS created, the creator of Ruby, it's built in C. However, it's not capable of parallelism. So threads cannot be run all at the same time. Threads can only run one at a time. So basically we have something called the global interpreter lock. And the global interpreter lock essentially makes it so a thread can only run one at once. So it'll constantly switch back and forth between threads, but only one thread can be run at one time. So it's important to know that the standard version of Ruby cannot actually do parallelism. It can do concurrency, but not parallelism. All right. So with that all said, with getting processes and threads and concurrency out of the way, let's get to some actual examples of multithreading to kind of show you how to actually use multithreading in your work. So if I go here and kind of clear this out. So right here, I have a simple program. All it does is I have a method that defines, or I have a method called output. And what it does is it sleeps for a second before outputting a number that's given to it. And so we're going to loop 1 through 10 and then just call the output number. And then we're also going to test how long it takes. So this one's going to take a little slower because it's moving one at a time and it's sleeping. So we can see that right here. Do Ruby 1. So you can see it's running one at a time and it's pretty slow because it's waiting a second before outputting each number. And by the end, you're going to see it took about 10 seconds to run. So you can kind of imagine this to be a program. Let's say you're running a program that has 10 different things it needs to do. So what you could do, like maybe it has to do 10 API calls, 10 third-party API calls. You could do it one at a time, but you can see it's going to take it's going to be pretty slow if it is one at a time. So what we can do actually is to enable multithreading and use multithreading in this program to make it run much faster. So in Ruby, the way that we do multithreading is we're going to use the thread class, which is very convenient. So what we do is in each loop, we're going to do thread.new, and we're going to pass a block to it. So this block, the thread executes the block that's given to it. So whenever I call thread.new, it's going to execute this block in a separate thread. Oh, sorry, again, my cat's making noise. Anyways, so we're going to execute, so it executes this block whenever it's given. And so this right here, this is a very simple change. There's still a little more we could do to make this work. However, I want to show you what happens when we just create a thread to kind of show you why it's not going to work fully right now. So if we run this right now, oops. So there, you can see that it ran really quickly, but it didn't do what we wanted to do. It didn't do what we wanted. Because you see right here in the first one, it outputted all the numbers, but we don't have any numbers here. It just went and finished quickly. So, but why? Why did that happen? Why didn't it execute? So the reason for that, I can show you, is because threads are synchronous. So when a main thread, so when your main process spins up new threads, it has no knowledge of those other threads. It doesn't know what's happening. It knows that it knows that they exist, but it doesn't care what's happening. So if you know JavaScript, you know a sync. Whenever you do an async call, it does it on its own. You don't know what's going to happen. You don't know when it's going to finish. So what's happening essentially is when this program runs and when we loop 1 through 10 and create 10 different threads, the program keeps going. It goes to then line 12 and line 13, and then it stops. So once it's output this number, the process finishes. And so the important thing to remember is that the process is the overall arching thing. So once the process stops, all the threads stop as well. So if we don't tell the process to wait for all the threads to finish, it'll just finish and all the threads will just die off. So that's why that's why the threads aren't working right now, because they were stopped too early. So what we need to do is we need to tell the program to wait for all these threads to finish before going on. So the way we do that is by creating a thread array. So whenever you create a new thread, whenever you call this thread.new, it returns a new instance of a thread. And so what we're going to do is we're going to create an array of threads. And then whenever we create a new thread, we're going to append that thread to our array of threads. And now what we're going to do afterwards is we're going to loop through each thread, and we're going to call the method join. So what this is doing is it's telling each thread that once it finishes, to join back with the main thread. And so what happens is when this program hits this line, it stops and waits for each thread to finish before moving on. So it will wait for each thread to finish before going to line 15 and 16. So in JavaScript or Node, this is similar to async and await. Whenever you run await, it waits for the asynchronous call to come in. So now if you run this, we can see that it does in fact work. There we go, 1 second. So it ran 10 times faster than our previous example. But there's one crucial thing to notice, is that each of these numbers were output in different order. And the reason for that is because I mentioned before, threads are asynchronous. There's no way of predicting when a thread will finish, because threads don't finish in the same order they were created. As you can see here, number 1 was the first thread we created, but it didn't finish until maybe the sixth position. So it's a 6th thread to run. And so you can run that again, you can see it. It's going to be totally different again. So you can see some crazy, wacky numbers happening. So threads don't finish in the same time that they're started. They're all asynchronous. So it's important to know that while multithreading will definitely speed up your program, if your program depends, if you have 10 different tasks and all of those tasks need to be completed in order, multithreading might not be the best option, because multithreading is used. It's the best use case is when you have multiple tasks that don't depend on a specific order. Another thing to worry about with multithreading is when you have all of your threads trying to access the same piece of memory at the same time. So the reason that's possible, as I mentioned before, if you look over here, yes. So each thread shares a heap, meaning that all of your threads can access the same memory. Each thread can access the same pieces of memory. So what happens when you have all of your threads trying to access the same variable, or trying trying to write or manipulate the same object at the same time. A lot of weird things can happen. You can get corrupted data. So that's known as a race condition. When you have multiple threads trying to access the same piece of memory at the same time, they're essentially racing each other to see who can do it first. And so you can get a lot of weird results that way. So I kind of show you that race condition in action. So we can go to counter example. So in this little app right here, I'm implementing a simple counter. So the counter starts at 0, and we already have the multi-threading here. So we have the threads array, we have the loop of 1,000, and so each thread is going to get appended to the threads array, and then we call join each thread. But you can see here the block that we're passing into each thread is the same before. We're sleeping for a second to kind of simulate some work that's happening, and then we're going to increment the count by 1. So we're doing quite a few threads right here. We're doing 1,000 threads. So a lot of things can go wrong when you have 1,000 threads trying to access the same memory at the same time, the same variable at the same time. So just take a moment and kind of imagine what you think is going to happen before I run this code. Just kind of guess what you think is going to happen. So let me run this. You got your answers? Let's see. Huh, it worked. Yeah, count 1,000. Why is that? Let's try it one more time. So yes, so this works right here. However, the reason why it works is because we're using the standard version of Ruby. So as I mentioned before, kind of go back and forth a little bit. The standard version of Ruby has a global interpreter lock. So only one thread is going to be run at one time. So only one thread is ever going to access a piece of, is ever going to access a variable at one time. So we're not gonna. So luckily, it's kind of nice. In the standard version of Ruby, the global interpreter lock prevents us from having the majority of race conditions because it runs threads one at a time. But we might not always be using Ruby in our day-to-day job. And might not always be even using the standard version of Ruby. So for the sake of argument, let's imagine that you're using a different language. So you're using Go, using Python, any other language that enables parallelism with multithreading. What do you think would happen here? Luckily, I can actually show you because there's actually a different version, a different runtime of Ruby that enables parallelism as JRuby. JRuby is written in Java. It's written on the JVM. So it actually enables parallelism. So what I can do is I can actually change the runtime of Ruby to use JRuby here. So now we're using JRuby to interpret our code. So again, take a moment, think what's going to happen, and kind of I'll show you what we're going to get with this. So take a moment to think. All right, got it. Let's see if you're correct. So ignore these warnings. These are all just the Java code. All right, so we have a count of 782. So something went wrong here. So something, what we're having is essentially we have a bunch of threads all trying to access the same memory at the same time. And so they're overwriting each other and they're making it so it doesn't increment correctly. So you can show you this right here. So we have a race condition essentially. So what's happening is we have one thread, or we have multiple threads all reading the same information and trying to increment at the same time. And so when they rewrite the data to the variable, you have the same number happening multiple times. So what should happen ideally is thread A pulls 17, increments it, writes 18, and then thread B then pulls 18 and increments it and does 19. But since we have parallelism happening, all these threads are overwriting each other and we're getting corrupted data. In this case, corruption just means inaccurate, but we're getting inaccurate data. So how do we fix this? How do we go about fixing this issue? So we have, in programming, there's something called a mutex that we can use. So a mutex stands for mutual exclusion object. And if you're ever in elementary school or when you're a kid, I think a lot of us had a scenario where we're at summer camp, or if you're in a classroom and you're in a scenario where everyone wants to talk, but the teacher makes it so only one kid can talk at a time. And what they do is they give whoever's speaking a special object. So maybe a teddy bear or a fancy stick or something. They give them some object. And so whoever holds the object is the person who can talk at that time. And then when they're done talking, they pass it to someone else. So that's essentially what a mutex is. Whichever thread, you can see right here, whichever thread holds the mutex is a thread that can access the resource And then once it finishes, it releases the mutex so another thread can access it. So essentially, a mutex forces each thread to wait one at a time to then increment the data. So how can we use a mutex to fix our race condition here? So luckily, Ruby also comes with a mutex class. So all we need to do is do mutex.new to create a new mutex. And then we're going to surround the vulnerable code. So the code that is vulnerable to race conditions, we're going to surround it in a mutex block. So it's going to call mutex.synchronize. So we're going to surround the code with mutex.synchronize, and that's all we need to do. So a 3-line change, all of a sudden we have thread safe code. To prove it to you, let's try it out. So count of 1,000. Let me try again to prove it. So right there, count of 1,000. So you might have noticed that it was a little slower running with the mutex because, since we're forcing each thread to wait to increment the data, we are introducing a little more latency into the program. However, it's still much faster than if we were to run it one at a time, because since we are running 1,000 threads all at once, we have to wait a second for each thread. So we'd be waiting 1,000 seconds. So we'd be waiting here for a while if we run it one at a time. So even though we had to introduce a little more latency, we made the code thread safe, we made the data accurate, and it's still pretty dang fast. So that's pretty good. So now that I've talked about, talking about how to create new threads with the thread class, I've introduced mutexes and how to use mutexes to prevent race conditions in your code. Let's combine these together into a real life example. So I mentioned the synopsis of this talk that I want to finish with a demo from my real life experience at DigitalOcean. So recently I had to create a low latency API for our new product that we're creating. And the API had essentially 2 requirements. It needed to be really fast. So ideally response times would be less than a second. So whenever a user requested that response or requested that endpoint with an HTTP request, they'd get their data back in less than a second. So that'd be really good. And the data had to be as accurate as possible. So we don't want to give the user false data or fake. Yeah, we don't want to introduce any data corruption in our API endpoint. So I've written a little example Sinatra API right here to kind of simulate what I was doing. So in this example API, we have an API endpoint that is going to return information about GitHub repos. So in this case, I'm using my own GitHub repos just because I didn't want to make it too nice or too fancy. I'm hard coding the API repos. But this is definitely a real scenario you might see. So in this case, I'm pulling the token. So I'm pulling the GitHub token from the environment. I'm not hard coding it here because I don't want you guys to steal my API tokens, but so I'm pulling it from the environment. And then I'm pulling the repo information. In this case, I'm pulling it from a file, but I'm meant to kind of simulate pulling it from a database, because a lot of times when you write API endpoints, you're going to be interacting with the database. It's a little too much to create a database for a Sinatra application, so I don't want to do it. But in this case, I'm pulling information from a file, and so you can see here, it's just my own repo information. So these are just my own GitHub repos. So once it pulls the data from the quote-unquote database, it then loops through each of the repos and makes a request to the GitHub API. So you can see it's the GitHub API. And it returns, so the data returns, it parses it out, and then it creates a hash of the information. So you have the owner, you have the repo name, and you have the number of stars, number of forks, the watchers, etc. And then I append that to the result array. So this array is what I'm returning to the user eventually. So this endpoint is going to return an array of GitHub repo hash objects, essentially, or JSON objects. That's what we're returning to the user. And so you can see here, the reason I'm putting slow response is because we're looping through these repos one at a time. So this is going to be a little bit slower response. So I can show it to you right now. So I go here, and I can run the server for Sinatra. So once it starts running, there we go, it's running. Let's clear this out. I'm going to do some curl requests against my API endpoint. So I'm going to curl, and so the API is running at localhost 4567, and we're going to do slow response. And so you can see here, actually in the response, I put how long it takes for this to come back. So we'll see how long this API endpoint takes to run. So So you can see it's it's running pretty slowly. If your users were running if your users were interacting with this, they would not be too happy. So it's taking quite a while. There we go. So you can see it took about 11 seconds to run. And so that is definitely not what we want. If your users were interacting with an API endpoint that you're creating and it takes 11 seconds every time to get your data, they wouldn't be too happy. So what we can do to make this faster is what I've shown you before. So I have this fast response here. And so we can use our mutex, we can use our threads array, and we can use multithreading to make this much faster. So you can see here, I have the threads array, and as we loop through the repos, we're going to append the thread, each new thread to the threads array. And so each thread is tasked with calling the API endpoint and then returning it. So it's a task with calling the API endpoint and returning the information. And then we're going to so the reason we're using a mutex here is because each thread is going to be accessing this result array. So each one is accessing a shared piece of memory. So to prevent any sort of race condition, we want to surround this appending into a mutex block so that we don't prevent any kind of race conditions happening. And then as before, we do the thread.join, and then so after that, we're then ready to return the data to the user. So kind of go over again, pull the information, we loop through the information, and we're giving each thread the task of getting the information from GitHub and then appending it to a shared array. And then we're going to turn that array to the user. So let's see how quickly this runs. I'm going to change this to fast response. You can see this pretty quickly. So it was about half a second. If we try it again. So the time's right here. So that was pretty quick. 4 seconds. Let's see if we can actually make it go a little slower. So we're pretty quick right now. So this is doing pretty quick. So that's definitely what we want. This is 0.4 seconds. You know, your users would be very happy with an API endpoint that returned in less than half a second. In previous practices with this, there have been times when it has returned slower. You know, our program is dependent on the GitHub API. So if the GitHub API is running slowly, there's a chance that our endpoint might run slowly as well. So let's do it one more time. It's been pretty quick today. So I was hoping it'd be a little slower because I want to show you another improvement that we can make. So this right here, this is definitely good enough to put in production. You know, using a mutex, using multithreading. However, there is another way we can format this code that we can actually avoid using this mutex altogether. And what we can do is actually just not use that shared resource in it at all. So I have this fast response here, and what we can do is, so I have this, before I had the result array, but now what we're doing is I'm gonna when we loop through all the repos, I'm gonna call map, and so that's gonna return an array of thread instances. And so once this finishes, this result array is gonna be an array of threads. And so what we're gonna do is we're actually going to, in this case, each thread, instead of appending the data to a shared resource, we're just going to return the data. So whenever a thread finishes, it's going to return that data block. And so what we're going to do here is, now that we have this array of threads, we're going to map through it and call value. So before we've been calling join, but this time we can call value. And what value does is, since we're mapping through this array, it's going to return a new array with the return values of each thread. So when we call value on a thread, we're going to get the return value. In this case, the JSON block. So in this case, the data hash. And so we're going to be returning an array of repo hashes, which is exactly what we wanted. So if we run, we can do this here. So this was faster response. Fast response is still being pretty quick. So let's see if fast response is even faster. Yeah, so it's actually pretty quick too. 0.5. Let's try it one more time. It's a little slower. So I guess today fast response is being a little faster. Usually this one's a little faster, but today it might be a little different. Yeah, so it's still pretty quick. Overall, using multithreading is definitely going to speed up your code no matter what. And if you can avoid using mutexes if possible, it'll definitely simplify the complexity of your code, because when you introduce shared resources and when you introduce mutexes, it does make your code a little more complex because you have to worry about race conditions. So if you can format your code in the way that you avoid race conditions altogether, it would be the best option. So yeah, that is essentially the talk for today. I just want to show you guys, multi-threading, kind of give you a real life example. And yeah, so that's what I had for today. But let me go through any questions you guys have. So I'm going to look through the Q&A section. So Tanner asks, you mentioned that your comp can only run as many processes as there are CPU cores, but PSOX output far more. Yeah, so that's correct. So the reason why it's showing, so when I run PSOX, so if I just do PS right now, if you run PS, it'll show you just the processes you have. So I think right now I have iTerm. I have a couple iTerm tabs, and I probably have, there might be maybe Atom in there somewhere. But so we can actually look at the description of Ox. So this kind of talks. So this gives us the status of a process. So if you just run PS by itself, I think what it does is just shows you the current process running. So by doing PSOX, it shows you all of the processes that are running even in the background. So as I mentioned before, a CPU core can only run one process at a time at any given moment, but it can definitely switch back and forth between different different processes. So for example, Atom might have a process open for just Sinatra app. So right now I'm running the Sinatra app process, but when I switch here, it's going to switch now to counter process. And if I switch here, it's going to switch to this process. So each of these tabs might have their own process, and it might be running one process at a time. But if I switch them back and forth, those processes get switched as well. So the reason why you see a lot of processes when you run Ox is because you can see here display information about users. Let's see. So A is the first flag. Then we have U somewhere here. U. Display processes belong to a specified username. So when we do PS Ox, it shows us the username correlated with that process. Yeah. So these A, U, and X are the processes that we show. So yeah. So PS just shows us I think PS just shows us the current running process, so the status of our currently running process. But if you do PS Ox, it shows you just all the processes that you have, even in the background of your computer. So it's kind of cut off right now. Do that again. There we go. So you can see I have multiple tabs right here. So I'm pretty sure the reason why there's so many GitHub or Google Chrome processes is because each tab corresponds to its own process. So hopefully that answers your question. All right, so Jenny asks, what's the maximum number of threads a process can run at the same time? What are the factors that limit the number of threads that can run at the same time? It's a good question. I think it's kind of based on your computer. So it's based on so whenever you create a new thread, you're adding more memory because the thread has to live somewhere, and the thread's it's gonna live in memory. So I mean, you saw spinning 1,000 threads, it didn't really do much to the computer. It might have taxed it a little bit, but the threads weren't doing too much data processing. I think it's kind of a combination of how many threads you're spinning up, because each thread is going to have its own memory footprint, but also the amount of data or the amount of work that each thread is doing. Because if you spin up 10 threads, but they're each doing processing petabytes of data, it's going to definitely run up the CPU percentage on your computer. You can see right here actually in PSOX. If I do this, sorry, and I go to the top, it shows you how much CPU or the percentage of CPU each process is running. So you can see right here, Zoom is taking up half of my CPU and about 2% of my memory. So it has a pretty small memory footprint, but in terms of how much the computer is working to work it, Zoom is definitely taking up a lot. So if I were to spin up another process with 1,000 or 1,000,000 threads, all of them doing a lot of work, that would definitely take up more than this. So the computer would have to allocate more resources to that thread, as opposed, it would take it away from Zoom. So Zoom might lag behind if it's kind of focusing on that process. So I think it definitely depends. I mean, I'm not totally sure there's a maximum number. There might be a maximum number. At the moment, not totally sure. But a lot of it depends on how much memory is free and how much memory is free to be used by those threads being run. We also have a couple chat things. So by default, it would be right. So I'm just looking at the chat right now. So Tanner asks, each of these GET requests are synchronous by default and rewrite. So each iteration of the block will be blocked until, I think it's just, I'm sure this is a joke. Yeah, so I mean, Ruby is definitely a little bit different than Node. I think it's more of a Node question. But yeah, so it seems like we had 2 questions so far. And if there aren't any more questions, then yeah, we'll end it here. I hope you guys definitely enjoyed this talk. I hope you learned quite a bit. And feel free also to reach me out in Slack if you have questions later on, just to chat. So yeah, hope you guys had a good time. Or we got one more chat. Oh, thank you. Thank you everyone for who learned a lot. So yes, I will stop. So Surgeon, let you know you can stop now, and I will also end this talk now. So I'll stop sharing. But